Hey everybody. Shall we get started? How was Carnival? What interesting events unfolded? You saw me? Yeah? I was hanging out at Carnival a bit. It's good. I was checking out some booths. Let's see, anything else? Oh, so we have that exercise I'd like you to get in by tonight. We have project proposals that I'd like to get to have you in by tomorrow night. Okay, so stretch run. Remember, exam 2 is a week from today. So, yes.
Is it at night also?
Yeah, exam 2 will be under similar conditions, which reminds me I need to get a room. Which reminds me I need to get a room. Okay, any other questions about stuff going on? I started listening to Bollywood songs on Saturday night when I saw Three Idiots at the recommendation of a student of mine. And it was pretty awesome. And I actually noticed they're not going to have it on Amazon streaming after next week, so you only have one chance to see it. Okay, all right. So today what I wanted to talk about, today's a new lecture in the class, so this is kind of experimental. I'd like to talk a little bit about high performance evaluation of deep networks, which many of you in this class may actually know a lot more about this than me, so let's see how this goes. One thing I'm going to try and do today is I'm going to focus today on inference, on forward evaluation of these networks, for those of you that know what that means. And on Wednesday, I'm going to come back and actually focus on large-scale parallel training of these networks. So we're going to focus on inference right now, which is typically a single node problem. And we're going to talk about training next time. And in some ways, you could say, well, training's a lot more important because training takes forever, and inference just takes milliseconds. But I chose to do it this way, and we'll see how this goes. OK, so how many of you have even heard of a deep network? Most people might have heard of a deep network at this point. How many people have implemented a deep network? A couple of people have implemented. How many people have used sort of off-the-shelf deep networks? How many people have trained something? OK, so a lot of people have trained something. OK, very good. And what did you use to do the training, actually? What packages? What software? Caffe? Oh, and Theano. OK, cool. OK, so the reason why everybody, the reason why there's a million students in our machine learning classes these days, the reason why folks are very interested in these workloads is that it's absolutely true that a lot of modern advances, literally in the last couple years, in various types of AI and machine learning, whether it be for image understanding. So you've probably heard in the tech press about all the results of, we're getting much better at understanding the contents of images. So in this case, a deep network is actually captioning the photo, as in you just give it as input a photo, and out comes a caption about this is what's happening. You've seen results of of image classification. You give it an image, tell me what object is in this image. A lot of the same technologies are being used to do natural language processing and speech processing. Just not so long ago, you heard about using deep learning. I was all over the tech press due to Google's DeepMind and the GoPlane agents. So there's also a lot of terminology in this space. It can get a little sort of tricky to sort out. But at the end of the day, actually, some of the concepts that's powering all of this stuff is incredibly simple if you think about it from a parallel computing perspective or a systems perspective, rather than from the mathematics of machine learning. And of course, you really need to understand both of those, but I can only tackle one of them today. So I'm going to try and give it to you completely from the system side today. Completely from the system side. And I'm going to assume nothing about have you had a machine learning class or anything like that. So at the end of the day, or at the beginning of the day, I guess, what these deep networks are they're just made up of a bunch of computational units. So I've drawn here a very, very simple unit. It has 4 inputs. It has 1 output in this particular case. And so there's values on the 4 inputs, x0 through x3. You can think about a unit as just being a function. That function takes the dot product, or weights all of the inputs, or modulates the inputs x0 through x3 by the weights w0 through w3, and adds a bias to that. So you can think about it as literally just performing a dot product, adding a bias, and then sending the result of that through some other function, which in the context of this lecture, I'm going to use a common function that's used for in image computer vision networks, which is the max of 0 or the value x. So if the dot product is negative, if these weights are responding inversely proportional to their inputs, I'm basically just going to squash the output. I'm going to call it 0. Otherwise, I'm just going to pass it right through. So this is a linear transform on the input, followed by a nonlinear operation of some sort. So this is, in the context of this lecture, I want to call this one unit. And I'm going to be a little hesitant to call this a neuron because your brain does not have these. Right? So, but you'll hear the term neuron used interchangeably with with the concept of a unit. And there's a bunch of different ways you can think about what I have on the slide right now. If you want to think completely like a computer scientist, what are you thinking? Is there an analogy that sort of is coming to mind? I have a black box. It takes some inputs. It has an output.
I was going to say MapReduce, I guess, because it's like
Oh. Well, that's even a more complex analogy. I mean, you could just think about it as a function on 4 inputs to an output. You can think about it more, if you want to think more mechanically, you can think about it like it's just a circuit, right? It has a circuit, it has 4 wires coming in, and it has an output going out. It's a circuit. Another way we can think about it is if we want to draw the analogy to biology, you can think about the analogy of this circuit trying to simulate in some really, really coarse way the behavior of a neuron in your brain. So you can think about the output of that circuit, it's a cartoon diagram of a neuron. A neuron will receive electrical signals as input and then produce an output. It itself is a function. So the output along the axon is a sort of in rough correspondence with the output of my neural network unit. And the inputs to the unit are modulated by these weights. And you can think about that as other neurons feeding their input into this neuron. And at the connection, sort of there's like a sensitivity along these channels called dendrites, right at what's called synapses when these things connect together. You can think about these weights as being some really, really gross modeling of the sensitivity of the output response, the signal sent along the dendrites as a result of inputs coming in from other neurons. Okay. So when the word neural network is almost historical in that some of the folks that originally did this work decades ago were very much inspired by modeling how the human brain works. These days, the connection between this is what a unit does and how the brain works is very tenuous at best. But the legacy of calling this a neuron still exists. So in one sense, you can think about it as a circuit. You can think about, well, it's kind of like trying to model the operation of the neuron in a brain. Or actually, you can just give it a straight-up machine learning interpretation, as if I change my nonlinear function here, f, to something like a sigmoid, then I'm taking any value on the real numbers and compacting it to the 0 to 1 output range. And I can interpret the output of the unit as a probability of something happening. So I can think about the neuron as basically being a binary classifier in this case. That if the sigmoid says that, oh, there's, it's very close to 1, I can say that it's really high probability that this is an instance of class 1 and not an instance of class 0. So it's perfectly reasonable to think about one of these units in any of these 3 ways. I tend to think about it just as a circuit. And we're going to start composing these circuits so that together they can perform much more interesting functions than, for example, binary classification, and so on and so on. Okay. So I can start to compose these things. I can start to compose these things into larger networks. So every gray box I had on on this slide corresponds to one of these units here. So imagine I have some input. I have 4 input values. And I've created a network where each of these black boxes perform some computation subject to their weights. and their bias, and their outputs get fed in to more units, and so on and so on and so on. And the output of this, in this particular case, is just one value. So in this case, you can think about this as a much more complex network, which at the end of the day outputs one value, which if you want to interpret it as a probability distribution, you could. And the reason why the term deep comes in is that there are at least one layer of these units that are not the input or output layer. So they're referred to often as hidden layers because they are not manifest in the definition of the machine itself. This is the input, that's the output. These are the innards in how this function computes its result. And of course, in this diagram, I've happened to draw a wire, to draw a link between every input and every layer 1 neuron, as well as a link between every output of layer 1 neurons and every input and every layer 2 neuron. So this is an example of where I'm saying, look, information from any of these neurons might impact, or these units might impact the output of any of these other units. And of course, that need not be the case. I can make a completely different network. For example, this one right here, where notice that now between these two layers, there are only sparse connections. There's only a few inputs that end up triggering the behavior of this unit here. So there's a lot of locality in this computation. Okay, so yeah, so this red link, this would be a fully connected layer. This would be a layer that is much sparser. Every input only impacts 3 outputs. Or another way to think about it is that every layer 1 unit only receives inputs from a spatially local region right around it. So this is, there's nothing fancy here, right? Like I'm drawing circuits. Does this make where everything's okay? All right. So now I want to take a small aside, and I want to bring you back to the image processing lecture. So remember my simple this was a 3x3 2D convolution from the image processing lecture. We talked about various ways to implement that efficiently. I don't have any of those optimizations on the slide right now on purpose. Okay. So every output pixel is the combination of the values of 9 input pixels in this case. And here what I'm showing you on the slide there, or on the top right, is I'm showing you for every output pixel, which is colored red or blue, or yellow or blue, I'm showing you the support region, the pixels of the input that affect that pixel of output. Make sense? And if I wanted to draw those dependencies, that's pretty interesting, right? Is that if I think about every pixel of my input as an input to a network, and I just draw the dependencies, I could think of the convolution as essentially performing, let's go back to this diagram here. I'm performing this dot product of the weights, which are the convolutional weights, the weights in the filter, against some number of inputs. All the inputs connected into a particular unit. And if you look at how I've wired up this particular network here, notice that I have the 3 surrounding pixels going into the inputs to the units that correspond to every pixel of the output. Now, one little aside is I drew this diagram in 1D, so I have three inputs, and in practice there should be 9 because this is a 3x3 convolution. But it would have been a nasty diagram to draw. Okay. So there's one difference between the network that I proposed here and a convolution. So here, every one of these units have a different set of these W's. Every unit has state, and it can have its own weights. Now, what's the difference between that and what's going on in a convolution? It's the same weights, because I'm multiplying. So if I go back to my convolution code, for every pixel, so one way to think about that is for every pixel or for every unit in this layer, compute its output. And its output is, in this case, the dot product, iteration over all input links, times a common set of weights. So everybody see that? So even though you can think about this as a network, as a sparsely connected network, it is a convolutional layer, which means that all of these gray boxes share the same state, which are the weights. So I can implement the evaluation of this network as a convolution if I so chose to do so. Make sense? Okay. And of course, I can do some other things, like imagine that I didn't want to produce every pixel of output. Let's say I wanted to run a convolution where like I chose I computed the output at 1 pixel, and then I skipped a couple of pixels, and then did the dot product around there, and so on and so on. So what I did here is all I did is I decided to compute the output at every other pixel. So I have stride 2. And notice that the size of the output is now half as large as it was before. So before I had width -1, height -1 was the output. And now the output is significantly smaller because I'm sort of just performing this dot product sort of sparsely throughout the image. And the only thing here is I just changed my loop indexing a little bit. Notice that I'm writing to j over stride and I over stride. And that's all I was doing there. And notice that the allocation of output now is width over stride and height over stride. So here's an interesting question. What does convolution with this set of weights do? So now I'm just drawing the weights as a matrix just to make it a little bit more easy. This is the exact same. It corresponds exactly to what I put here on the slide. So if I convolve an image with this particular set of weights, what do I get out? Yeah. Sorry? Well, this was not a Gaussian blur, but I agree with you that it will blur the image. Yeah. Yeah, this is a box filter. So if you were a signal processing person, you would say this is convolution with a box filter. If you're a graphics person, you might say it's something like it's a box blur, which some people might know what it's about. So if this is my initial input signal, and I convolve that input signal with my 3x3 filter, with those weights, you will exactly get this image. And this is just a zoomed view of that. And it's just a blurry image. You can see a little bit of structure there because of it's a box. So here's a different question. What does convolution with this filter do? Yeah. This is a lot more of a Gaussian. So the weight falls off as we are combining input pixels that are farther away from the output. And it would have been more obvious if I drew something larger than a 3x3. But if I take this filter and I convolve it against this image, I get this output. And you're going to get, if you look over here in the zoom view, you get a much softer, much blurrier, or a much smoother blurry image. It's actually much more pleasing. I can go back and, oops. Might be hard to see, but you can see there's still like some structure there in the box. And if you look here at the Gaussian, you get a nice, what you would think of as a proper blur. It's almost like in some ways, like your lens is out of focus or something like that here. Right. Okay, good. All right, so let's make it a little bit trickier. What does convolution with these filters do? And those of you taking my graphics class will know the answer to this, so let's be a little careful and let people that haven't taken my graphics class. Yeah. Edge detection. So how did you, that's a big leap. So explain to everybody else what you're thinking. I agree. I would say it's actually not exactly edge detection. I can be more precise, but yeah. Yeah. Assuming you didn't know it off the top of your head.
The middle pixel, it's after the convolution, we have the difference between pixels to its left and pixels to its right.
Yeah.
And so if the pixels to its left are very different from the pixel on its right, then we should see a large value, or an extreme value there.
Mm-hmm.
So we can...
So here's a thought experiment that'll help everybody. Yeah, I agree with you completely. Imagine the input image is all the same color. Okay, so imagine the input image is all the same color. What will be the output of convolving with this filter? Yes. It'll be 0, right? Because we're going to say, okay, we're going to take the pixel to my left, or to my top left, and I'm going to multiply it by -1. Then I'm going to add in the pixel above me, multiplied by 0. And then I'm going to add in the pixel to my top right, multiplied by +1, and so on and so on. And you can see how this is going to add up over this entire dot product to 0, right? And in this particular case, it's useful just to think about what the partial sums are across the rows. Every row will be 0. Now imagine that the input is a picture that's half black on the left side and white on the right side. So if we are completely in the black region, what is the output of the convolution going to be? It's going to be 0. It's just like if the image was all the same color, right? Same thing for if we were completely on the white region. What's going to happen if we are trying to get the output of the convolution at a pixel that happens to be right on the edge between white and black? Is the output going to be 0, or is it going to be something else? Something else. And what is it going to be? And why is it going to be something else?
Because the pixel to the right, the value will be whatever corresponds to white. So let's say it's higher than what corresponds to black. So the sums on the right side will be greater than the negative sums on the left hand side. So the overall sum will be positive.
Exactly. Another way you can think about this, if you've taken any numerical analysis class, what am I actually computing? I'm actually computing pixel to my right minus pixel to my left, which is what? It's a finite difference. It's a gradient. So this filter is actually computing horizontal gradients. Then it's actually adding up the horizontal gradients in each row. And so we're kind of getting an average horizontal gradient for the 3 rows right around the pixel. So I agree. So this picture, this filter is going to give out an output image that is non-zero if there is some horizontal gradient. What is this filter going to do? So it's going to do the same thing, but it's going to do it for vertical gradient. So this filter is going to produce a non-zero output for pixels where there is vertical gradient. Any question? No. No. Because here, this will have a response. If I had vertical lines, just completely vertical lines in my image, and that's it, the horizontal difference will be 0. Or sorry, if I had vertical lines, the horizontal difference will be non-zero. Excuse me. Because there will be horizontal gradients. Yeah. So here, this might help, actually. So I ran these 2 filters on my image, and this is what I get. Now, the colors come from the fact that I'm doing this independently on the red, green, and blue channels. So ignore that part. But the important part is, look how this picture is responding. It's non-zero. The output here is non-zero when there's it's a vertical edge, but it's a horizontal gradient. That might have been what was the tricky part, right? And here we have vertical gradients, which correspond to the bottoms and the top of the bricks. So it's useful. If you come from a graphic standpoint, you think of filtering and convolution as blurring images. If you think about signal processing, you may think of filtering and convolution as bandpassing images or selecting parts of the frequency content. If you come at this from a computer vision standpoint, it's actually very natural to think about a filter as almost being a detector for a particular phenomenon. And that filter, convolution with that filter, gives a high response when that particular pattern is in the image, the input image pixels. Right, so in the course of this lecture, it's very useful to think about convolution as response. Convolution with the filter is figuring out where in the image is there a pattern that matches the pattern that described by the filter. So I can repeat this process. So in this particular example on the previous slide, this is the response maps. These are the output responses of 2 different filters. In fact, these two filters right here. And I can have an arbitrary number of filters that I care about, a lot of filters, and I can run the single input image across all of those filters, and I can get out a bunch of responses. So I can think about convolution as taking, or convolution with multiple filters, as taking this 3D volume, which is height by width by 1 in this case, and producing another volume, which would be height by width by number of filters. And let's ignore the edge conditions for the width minus 1 and edge and height minus 1 stuff. We could always pad this out with zeros to make sure it doesn't shrink in size. So I'm going to ignore that in this talk. Okay? So I can apply a bunch of filters to an image at once. So here's an example of 96 different 11 by 11 by 3 filters. So it's 11 by 11 in space. It is 3 times 3 because it applies to R, G, and B. So it applies to the full red, green, and blue of the image. And here are 96 response maps that we sort of boosted. We've normalized and boosted the responses for each of these filters on this particular image. So you can kind of see what the filters are looking for by their own appearance. It's because the convolution is going to respond well if the contents of the image match up with the contents of the filter, right? Because if I'm multiplying numbers, I want them both to be high, or I want them both to be low. So these various filters, you can see them picking up various gradients and frequencies of gradients in various directions. And so this is the result, again, of me doing 96 independent convolutions on the input image. So I can build up this machinery a little bit more. I can take an input image, I can convolve it with a lot of filters, which produces a bunch of response maps. And then, remember at the start of this lecture, I said we were going to perform a dot product, and then we were going to take the output and manipulate it with some nonlinear function. And we use max as that nonlinear function. So for simplicity, instead of like sticking that max in here, I'm going to think about that max occurring between these two things. So I can take as input this big volume. I can just run per element. I can run that particular function on every element, in this case max, and I'll get out a new volume. And then I can do other things, like for example, I could downsample in the spatial dimensions to make a smaller volume. So this pooling layer is in this particular case, is taking 2 by 2 regions of every slab, taking the maximum response in those 2 by 2 regions, and sticking that in the output. So you can think about it as sort of a downsampling, but it's not an averaging downsampling, it's a maximum downsampling. So I've now created a bunch of just different operations, which I could also describe as a neural network. Right? So here are these convolutional layers. Each one of these I can think about as one of those units, this step, produce an output. All of those outputs are immediately sent through the nonlinear rectified linear unit in this case. Then I can have another layer which just takes the 2 by 2 region around of every part in space and downsamples that as well. So at least in the computer vision community, or at least the early stages of computer vision, things are moving a little bit away from this now. But you can think about all of these deep networks as just being sequences of these types of steps. Convolution, some nonlinear function, followed by downsampling. Convolution, some nonlinear function, followed by downsampling. And so on and so on. And so if that basically gives you all the tools you need to understand these large networks that exist for object detection and classification and things like that. So the one that really kind of got this started in the computer vision community was published in 2012. And it's a network that has 5 of these convolutional layers, followed by 3 fully connected layers. Or depending on how you want to think about it, you could call it 2 fully connected layers. And so this was the input image. You can actually just kind of read how it works off the chart. Here's the input image. So it takes as input a tiny little image, 224 by 224, hits it with 48 different filters, And in fact, they actually, the way this is drawn, historically, they actually split this up onto 2 GPUs because it was too big to fit on one computer. So it really hits this input image with 96 filters. You see 48 there and 48 here. So it does 96 different convolutions of stride 4, skipping every 4th pixel, against the original 224 by 224 image, which gives you out 55 by 55 images, responses, but there happens to be 96 of them. Then there's a downsampling, a pooling step, followed by more convolutions with 256 more filters, followed by a downsampling step, followed by convolution with 384 more filters, and so on until it finishes up with, sort of 2, or depending if you want to consider the softmax at the end, 3 fully connected steps, where the outputs of these about 25,000 units all go into these 4,000 units. These 4,000 units all have links to these 4,000 units. And then last, they go down to 1,000 units. And in this particular case, the output 1,000 numbers are just the probabilities of various categories of what's in the image: dog, cat, house, or whatever. So it's kind of that simple in some ways. You just wire up this huge circuit, you send in an image, you perform a bunch of convolutions on it, a little bit of downsampling, a little bit of nonlinear behavior, and out comes some numbers. And in this particular case, we interpret the numbers as probabilities of them being different objects, types of objects. And of course, since that time, like if you look at one of the more popular networks that many of you have probably used, for those of you that have said you've used this stuff, is there are 13 convolutional layers in this network, and 16 total convolutional layers. Conv, pool, conv, pool, conv, pool, conv, and so on and so on. So there's 16 layers in this thing. Okay, so what's the thing that I haven't told you, for those of you that have done some work training a network? Yeah. Well, but what does training even mean? So I haven't even mentioned training in this lecture yet. I've said how to create a circuit, create a function that a computer can obviously evaluate, and if you give that function 224 by 224 image, it spits out whether or not it's a dog, a cat, or a truck, or whatever. And most of the heavy lifting, in this case, is governed by what the weights are of each of these units. So 13 layers of convolutional weights, followed by a bunch of weights that describe the interaction between the units at the end. Where's the magic?
Firstly, compute a cost function.
Sorry?
Compute some kind of cost function that defines how well you classify the image.
Okay.
And then after that, you get some kind of real number.
Okay.
Basically, error that back propagates through the weights.
Okay.
You calculate all the differential.
Well, lost in all of that was the fact that I'm assuming that I have the perfect weights, right? Lost in all of that is this network has, I think, on the order of 60 million free variables, which are my weights. And if I had the right weights, I'm done. So training, what we're actually not going to talk too much about today, we'll talk about this next class, is the process of learning what those weights should be given a bunch of, in this case, given a bunch of examples. And we'll talk about how we can train those networks in parallel. But you can imagine that if I said, here's a black box, you have 60 million knobs on the outside of it. The black box will take as input an image, and it'll kick out a description of what's in the image. But you just have to turn the 60 million knobs to the right direction, to the right amount. That's what the training is doing. It's figuring out what the values of those weights should be so that when I shove an image into this network, the right answer comes out. So does anybody have a sense of why the heck these networks look like this at all? And in fact, it can be shown, I will not show it here, that the exact same representational power could be expressed in a single hidden layer that happens to have a little bit of nonlinearity. So what's going on with all of these layers? Does anybody have any, like, those of you taking computer vision, do they give you some intuition about this? Those of you taking machine learning, does anybody give it? Yeah.
The earlier layers are full of very primitive features that are extracting in, and then going into the very primitive features that have more complex features. That's the later convolution, and therefore, as you propagate through, we have one common categories, you can extract whatever you want from the highest.
Yeah, I mean, that's actually gets at a sense of it. And the short answer is we actually don't know how to train a network. We don't know how to come up with the answer of the weights if they have shallow topologies. That's kind of the short of the answer. But we can ask the question, well, what the heck is this? What has the network learned? Clearly, this works. So we can train. We have algorithms that can come up with these 60 million values. So what have they come up with at all? And maybe we could learn something from that to work on our own, right? So training a network, for example, is about 60 million weights, and we'll talk about that next time. So here is an interesting visualization. This is sort of what helped me the most understand what's going on. So what this is a visualization of, and again, before we go forward, remember what these networks are doing. They're taking an image, they're computing a bunch of different convolutions, so they're computing a bunch of different responses to different patterns. And then they're taking those responses, the outputs, and shoving them in as inputs to a new convolution. So you can think about it as, let's hit an image with a bunch of detections of little patterns, and then let's send those detections into another convolution, which is going to compute patterns in those patterns, and so on and so on and so on. So let's see what has actually been learned here. So what I'm showing you here is this is a visualization of images that triggered the greatest response of a particular unit at a particular layer. So this says that, in this case, these are there are 9, so there's 9 boxes here of similar images. So this layer 1 says that they picked 9 of the units, just 9 of the filters, and said that these images are the images that triggered the greatest response of these 9 filters. And what do you notice in these images? If you had to describe those images in words, what do they look like? They're gradients of various magnitudes and orientations. So the first set of convolutions, the first set of filters, is essentially responding to very simple gradients. Very much like the vertical and horizontal gradients that I showed you earlier, except these are 11 by 11 filters. What I'm showing you in the gray, so before we go forward, so what is layer 2 responding to? Because now layer 2 is a filter that's responding to combinations of responses of gradients. So layer 2 is saying I want a little bit of this gradient and a little bit of this gradient and a little bit of this gradient. That's what the weights are weighting. And what do you start to see? I agree with you that this would be really low-level gradients and just derivatives. What do you start to see in the next layer? Yeah.
Gradients in the gradients.
Yeah, I mean, you're either looking at second-order differentials, but like, you know, I could start to describe this as I start to see curves, I start to see circles and things like that. So some of these convolutions, some of the filters are basically combining the gradients according to some weights that start to pull out those patterns. And what do you see in the third layer? I mean, you start to see more complex patterns that you can actually, as a human being, begin to identify as stuff. You could say, hey, look, you know, this particular unit seems to be responding to wheel wells. Now, it doesn't know it's a wheel well. It just knows that it has learned a set of weights that combine various types of gradients that happen to correspond to things that look like wheel wells. What is this one? Sorry? Bird heads. And I could ask the question, is it actually responding to things that look like bird heads, or is it just responding to green backgrounds? it could. It could be responding to green backgrounds. In fact, it's actually not in this case because these gray boxes are visualizing what pixels in the input image that you see over there are most responsible for triggering that response. So if you kind of just follow the computation through the network, you can say that these pixels right here in the middle, like right at the top of the head, that curvature of the top of the head, that's the pattern that was ultimately causing this neuron to pick up on that phenomenon. So it's not responding to green backgrounds. It's definitely responding to the top of a bird's head, maybe on a green background. And if you just move up the stack, things get a little bit more human parsable as you move to lower and lower layers. So this is the output of layer 4. This is the output of layer 5. And again, every 3 by 3 block of images are top detections of a particular unit, or top responses of a particular unit, images that cause this unit to respond heavily. So I can't give you an answer on sort of, why do the networks have to be deep, but these visualizations do begin to provide some evidence of at least what has been learned, is that the depth allows us to combine increasingly more complex concepts to form even more complex concepts as we go forward. And that's actually why you see a little bit of a trend from the original successes being around 8 layers, moving to more modern networks that are 13 layers deep. Or sorry, 16 layers deep. Okay, so now let's get on to how do we actually make some of this stuff fast. Right, so now you kind of understand the workload, roughly why it is. And at this point, I'm going to take an aside into dense matrix multiplication. So I've already taken one aside into convolution. And now I'm going to take another aside into dense matrix multiplication. So everybody's probably multiplied 2 matrices. Hopefully I got this right. I'm writing this as C plus equals A times B, so I don't have to initialize C here. There's no C equals 0 anywhere. And so my claim is that this is a poor implementation of matrix-matrix multiplication. And would you agree with my claim? Or would you disagree with my claim? And let's assume, for the context of this lecture, that these are large matrices. So it does matter how we do this. So who thinks that this is a pretty good implementation of matrix multiplication? And one thing I'm going to put aside for now are the asymptotically improved algorithms that you've learned about in 251, like Strawson's, or less than O of n cubed. We'll come back to that in a second, but I want to put that aside for now. So let's say you can't change the algorithm. Is this good? Is this bad? Shaking your head, it's bad, or shaking your head, I can't think of a better way to do this. It's awesome. Well, it's terrible. Why is it terrible? And why am I okay for matrix A?
So because everything, like your whole cache line probably like on a single row.
Yeah, I have good spatial locality, that's true.
That would be okay, but for B, that would be problematic.
That's true, so I have very poor spatial locality of B. But matrix multiplication is actually another thing is temporal locality. So how much data do I read in a matrix multiplication computation? Like how much data do I fundamentally need to read out of memory? And to simplify this, we can say that everything is n by n for now. Yeah. Correct, but over the entire computation, let's say. Sorry? Quite a lot. Can we quantify quite a lot? Yeah.
n times 2.
Correct, yeah. So I basically just need to load every element of every matrix once, right? And if I wanted to simplify things, and if I just said, let's just say for now everything is n by n, I would have to load O of n squared amount of data, 3n squared, to get all the data through the processor. How much work do I do? Sorry? I do n cubed, right? I do n cubed work. So a perfect implementation of matrix multiplication would load every element from data from memory stored in an on-chip cache, if let's say all 3 of these matrices fit in cache, and it would use it n times. And if this was like n by n, like let's say this is 1,000 by 1,000 matrices, well, I would reuse every item that I loaded 1,000 times. My arithmetic intensity would be off the charts, and I'd be feeling pretty good about myself. In fact, I wouldn't care about temporal spatial locality at all. I'd be like, who cares? I'll read the cache lines inefficiently. I'm going to reuse the values once they're in 1,000 times. So I agree that our spatial locality in B is bad. Our temporal locality in C is actually quite good, right? Because I'm accumulating into the same value. And even though the spatial locality of A is quite good, the temporal locality is not so good. Because I'm going to read the whole row of A and come back, and in computing the element of C just to the right, I'm going to read it all over again. And by that point, it may be out of cache, especially if streaming through B evicted everything from A at this point, which is very possible. OK, so how can we do better on this? And this is something that everybody has seen because Professor Bryant gave a whole lecture on it. And you've had an assignment on this in another class. And what is the value of blocking? Like, what is blocking actually doing for you?
Yeah, same idea as the row that we did before. Like you want to re-access the same elements that you already loaded in the cache, even if they're not like on the same line or in the same block in the matrix.
Exactly. So let me go ahead and give you a block version of this. So this is the standard block version. My 3 loops just turned into 6. So I'm iterating over blocks. And then within the block, I am performing a matrix multiplication. So now you can see the innermost loops are computing one element, the white dot, from the block of C. And in doing so, it's going to read that white row of elements from A and that white column of elements from B. And then I'm going to move to the next sub-row in the block. And so on and so on. But when I come back and want those elements from A in the next iteration of the I loop, I have hopefully sized my blocks so that all of those elements of A are in cache. And I've hopefully sized my blocks so that all of those elements in B are also in cache. In fact, that spatial locality problem that you mentioned, that you didn't like, hopefully has kind of gone away in some sense now, because even though I read that whole cache line when I was reading that column of B, when I come back in the next iteration of the I loop, I'll hit all those values. And those cache lines are still in cache. Okay? So self-check here is, do you want as big of a block size as possible, and why? And what do I mean by this statement? How do you choose block size here? Do you want the smallest block size? Do you want the largest block size? Do you want the largest block size subject to a constraint? How do I choose this parameter here? And we can just assume that I'm going to use the same block size for all dimensions for now. Yes? Yeah, exactly. In fact, I actually don't even need C to fit because I'm basically using all of C and then going back and never coming back to it. So I definitely need all of A and B to fit, absolutely. And conservatively, you could say I need a little bit of C too. So do you want to make the largest blocks that can fit? Why is it good to have the largest blocks that can fit? Right, because the larger blocks that I have, my subblock matrix multiplication is block size cubed work for O of block size squared loads. And the larger I can make block size, the larger the ratio of those two values is. So there's always a tension in these computations. If a machine gives you a large cache, it's interesting in that it actually needs to have less compute, because you can crank up the arithmetic intensity by blocking into that large cache. If the machine gives you a tiny little cache, you actually have to have a lot of compute compared to bandwidth. Otherwise, you're more likely to be bandwidth bound. An interesting So I can do this. I can actually do this if I want to for multiple levels of cache hierarchy. And so those of you that have not ever implemented matrix multiplication, it is an excellent exercise to do. We don't do it in this class because it's kind of not the most interesting application, but almost everybody I know has always challenged themselves to do it. I spent 3 weeks of my life tuning up matrix multiplication at one point during grad school just for fun. And so like, it can become quite complex. And it's actually kind of unclear what the right answer is. So let me give you a few examples. It's like this doesn't even have SIMD. So how would you actually do SIMD in this situation? So this is pretty easy to parallelize, right? I just happen to parallelize it over the outermost loop. Who cares, right? I can go parallel over all the blocks, over the blocks of C. So multi-core parallels is pretty easy. Which loop would you actually vectorize? Which ones? The I and J loops? Yeah. I mean, now let's just make it simple. Let's parallelize one. So yeah, I think you could do that. Which one did I do? Oh no, I actually took K. You could do your way too, but when I did this last night, I decided to take K. So here's how I decided to do it. I'm not saying this is the best way to do it. I just decided to come up with something. Well, I actually parallelized over the, well, depending on how you want to think about it, yeah, I parallelized over the the outermost I loop. I actually chose the same loop that you did. Sorry, I was looking at the, oh, I don't know, yeah, I just spoke incorrectly. Yeah, I chose the exact same loop. So I'm now computing an array, a vector of outputs of C that are all contiguous. And I'm doing so by taking one element of A and multiplying that one element of A against a bunch of columns of B all at once. So you can see that here is load the value of C, load one element of A, and I just wrote this as splat, which is load one value and stick that value into a whole vector register. And then do a bunch of multiply adds, do vector with number of dot products simultaneously, but completely in serial for each dot product. So that's how I decided to do this one, and then I store the result out, which is pretty cool because now I have vector parallelism. It also improves the spatial locality problem and access to B because I use the whole cache line every time I grab it. But it's still not very good because I'm still walking over B in these really large steps, which I'm not very happy with. And just to, I don't want to get too much into it because it's not the point, is I can start doing a lot of other things too if I want to be a lot smarter. Like for example, I'm really unsatisfied with issuing a load of a single value here because I'm not using the memory system as good as I can. I want to use packed vector loads. So if you want to use packed vector loads, you start doing some crazy stuff. So the details of this you can think about later. But often we talk about transposing B, but it's actually easier to transpose A. And if you transpose A, you end up doing this crazy, you end up doing like this register blocking where you read down A and B just simultaneously. And you can use vector loads and vector stores, but you store the output transposed into C and you transpose it back later on. So things can get really, really complex here. Here's another one where I just decided to transpose B because the block size in the I dimension wasn't large enough for vectorization, so I just changed my whole algorithm to redo it for this new matrix dimensions. So the point is not that I want you to learn how to do this. The point is that it's pretty tricky. And if you look at a modern matrix multiplication library like MKL or OpenBLAS or Atlas, you'll see huge numbers of case statements for all the various input sizes to get the best possible performance. This is probably one of the best tuned codes on the planet. And it's not that hard when it starts. And it would be a full 2-week assignment in this class if I decided to assign it. Okay, so why did I tell you this at all? Let's go back to this convolution thing. It's actually possible to express convolution as dense matrix multiplication, which I just told you is one of the more optimized pieces of code on the planet, and it's pretty CPU or GPU friendly because if you do it right, it has very high arithmetic intensity. So let's think about convolving a 3 by 3 convolution. And what I'm going to do is I'm going to treat it as matrix vector multiplication. So I'm going to store my 9 weights. Remember, it's a 3 by 3 convolution here. And what I'm going to do is, remember, I need to compute all of these dot products. So what is a dot product? It's a row of the matrix times the column vector that's being hit by the matrix, right? So what I can start doing is I can start copying out of my original input array, out of my image. I can just copy these 3 by 3 windows and shove them into this matrix as rows. And I'm zero padding here just for clarity when I'm going off the input array. So that would be the first row. The next row would be I just slide the convolution 1 over, and my next row would be another set of inputs from the original input image. And again, when I hit this, when I do this matrix vector product, I'm going to compute the dot product of these weights with each of these rows, and I'm going to get out the output of the convolution in my column vector as output. So I'll just keep doing this just for the purposes of illustration. There's another row. And if I go down for this purple chunk, the purple chunk's the first chunk that has all actual values from the input array because it's offset by 1. So I can just build this matrix up. And now convolution is just matrix vector multiplication. So what happens if I want to do convolution with multiple convolution filters? How do I take this approach and keep going? Yeah.
As long as there's no nonlinear steps in the middle, you can just.
Oh, sorry. I mean, we're not even there yet. I'm thinking, remember, any one layer is convolution with multiple filters. I'm not talking about the cascade of layers in the network. I'm actually talking about, in one layer, I want to convolve the input against a bunch of filters, completely independently. And that's going back to this diagram. Remember, I have a set of weights, 9 weights if it's a 3 by 3 convolution. But I have, let's say, 96 of them. And I want to produce 96 different output responses. So I just showed you, and those were an example of the 96 filters. And I just showed you using matrix vector multiplication how to compute one convolution. So if I wanted to extend this to 96 independent convolutions, how would I do that? Yeah.
You would extend your weight vector to a weight matrix?
Exactly. So I have 96 different sets of weights. I could just extend my weight vector into a weight matrix, which would then be 9 by 96. And I can compute all of those convolutions sort of in one big lump. How? It's now dense matrix product. Exactly. So that would look something a little bit like this. So exactly as you suggested, I now have num filters, like 96 of these filters. The height of that matrix is 9. The width of this matrix is also 9. And dense matrix multiplication gives me a highly optimized, in some sense, implementation of all of these convolutions at once. Now, one thing I didn't mention is this is a single image with a single channel. And normally we'll take as input an RGB image. Or middle layers of the network take an image that has 96 different channels to it because it was the output of the previous layer. So we need to extend this one more time to figure out how do we compute the output when the input has 3 channels or 96 channels. And I'll just tell you really quickly. Is you can think about all of these channels being just different image planes, like red, green, blue. Or there could be 96 of these things if there's 96 outputs of the previous layer. And the convolution is actually going to do a spatial convolution in each of those in the spatial dimensions. And then it's going to just sum over all filter widths. So I'm computing essentially the average response out of all of those. And what I'll end up doing is I'll end up just stacking each of the channels horizontally in the matrix. Now, that set of weights, so it's a 3 by 3 by 3 set of weights. And now that all just gets dotted with all of the values independently, so I'm computing all of the convolution responses and then just summing them up, all as a matrix multiplication. Right, so this is basically the implementation of a multi-filter convolayer in terms of dense matrix-matrix multiplication, which you can then fire right off to a high-performance parallel library to do. So, yeah, so you can think about this as I'm convolving with 96 different filters and then summing them up, or sorry, 3 different filters or summing them up. It's probably easier to think about this as convolving with a 3 by 3 by number of channels filter, but the filter size is the exact size as the input, so there's no sliding to do at all. It's just one summation. You can think about it either way. Okay, so who thinks this is clever and who thinks this is stupid? So who thinks this is clever? It's pretty clever, okay. Who thinks this is stupid? You think it's stupid? It's actually pretty clever, I agree, but I also think it's stupid, so. Yeah, so what have I actually done here? I took this image, which was width by height, and I stored it as a matrix, which was width by height by 9, basically. Width by height by spatial filter size. So I exploded the amount of data by a factor of the convolution window. So for an 11 by 11 convolution window, like that original object detection network, I just exploded my footprint by a factor of 100. For more modern networks, the reason why they use tiny 3 by 3 filters is actually this reason. It's because so in some sense, you're like, well, wait a minute, I just blew up my memory consumption by a factor of, order of magnitude, 1 order of magnitude. It's a little concerning. Another thing that should be a little concerning is that I actually just decreased my arithmetic intensity because I have to load all this data. Whereas if I actually just sort of wrote the convolution directly, I would have just loaded the original image only once, presumably, if I did it correctly. So that may not be that big of a deal as long as the matrix multiplication is compute bound, because you don't care about extra bandwidth if you're not bandwidth limited. But we'll come back to that in a second. Okay. So memory footprint can be quite an issue here. So this is the VGG, these are all the layers in the VGG16 network, as well as the sizes of all the convolutions, bracket, with the number of filters in each of the layers. So when I say there's a lot of convolutions to do, there's a lot of convolutions. So input image times 64 filters, then take that output, hit it by another 64 filters, reduce, multiply by 128, by 128, by 256, 256, 256, 512, 512, 512, 512, and so on and so on, right? So there's a lot of different weights. So here's the size of those weight matrices if it is stored as 32-bit floats. And here is the size of the output volume. So remember, the input is the input image. It's convolved with, 9 megabytes of convolutional weights. And you get as output a 1.5 megabyte image after the downsampling and stuff like that. And remember, if you take the matrix multiplication implementation I just told you about, you should multiply all of these values by 9, because I have to take the output and construct the input matrix for the next layer to do the convolution, which can start to get up there, because like those first couple layers, that's 12 megabytes. Now all of a sudden, every input matrix is 100 meg, and all of these numbers are for processing one image. So if you want to process multiple images at a time, you then need to multiply these numbers per image. So if you wanted to say, do 8 images at a time, because maybe that's a useful way to vectorize, or you have a warp size 32 on a GPU, so you want 32 images at a time, you would need to multiply that 12 megabytes by 32, and then potentially, if you use the naive matrix multiplication approach, multiply it again by 9. So now we're talking about a gigabyte of memory for one layer of this network. So these issues can come up and bite you very quickly. So, and in fact, what I just described to you, more or less, with the exception of one package that a student just released 2 weeks ago, is how deep networks are evaluated on CPUs. There's no library you can go download that has a really good implementation of direct convolution, which would look something like this. Right? For all input images, for their height, for their width, for the number of filters, for all the channels of the input image, for 3 by 3. I think I got it right. I was looking at it a lot last night. So remember how hard it was, or I claimed, and you guys seem to have bought the claim, that it was difficult to optimize the 3 nested for loops of matrix multiplication. A conv layer is 7 nested for loops in a deep neural network. And so if you do it directly, there are some benefits. You avoid the cost of materializing the matrix or reloading these data, these values that you're copying into different places in the matrix a bunch of times. So that's good for bandwidth and also footprint. And in theory, you have higher arithmetic intensity if you block these loops as well as the expert programmer at Intel has blocked the matrix multiplication loops. And so that's kind of the state of affairs of how to implement these things efficiently. So there are a couple reasons why, okay, so that would be a fun exercise. And in fact, we have an assignment that we decided not to give you guys this year, which was go to town with this and beat Caffe. And it's a fun exercise. So those of you, if your projects go off the rails and you need something to do, 2 valid projects just popped up in this lecture. Okay, now just like with matrix multiplication, sometimes, especially at large sizes, you can think of, there's sharing in the mathematics, in the algebra, that you can exploit. There is also that going on here, which we haven't talked about. And I encourage you just to go read the papers, but I can give you a flavor of some of those solutions. One solution is those of you that are ECE or have done any signal processing, you should be going, wait a minute, convolution in the spatial domain, if I transform into the Fourier domain, that's just pointwise matrix multiplication. For large convolution windows, it turns out to often be a good idea to do the FFT on the input and then do all of these convolutions in the Fourier domain, if that is something you're familiar with. Another example, which is some work that's only really published has been well known in the signal processing community for decades, but was only kind of come up in deep neural network implementations, is another way of doing very, very fast convolutions. And I can give you a flavor of it in 1D, of what they're trying to do. So imagine you were doing I'm going to do this all in 1D. Imagine you were doing a 3-tap convolution. You're blurring every 3 items into one output. And you're trying to produce 2 outputs, 2 values of the output, y0 and y1. Well, if I decide to write this as matrix multiplication, it's pretty easy, right? It's saying that, well, y0 and y1 are just the dot product of the input numbers times the weights. Basically what we just set up. Okay? But you can actually rewrite this as just the sum of 4 numbers, which you can compute. I'm not going to derive it here, as there's a bunch of shared structure in this. So I can just compute these 4 numbers, M1, M2, M3, M4, and then all of a sudden those 2 convolutions just become 4 additions, where normally they would be 6 multiplications, 3 multiplications for every output plus 2 additions. So in this simple example, I've taken something that used to be 4 multiplies and 4 adds, and turned it into, 6 multiplies and 4 adds, and turned it into 4 multiplies, just this multiply, this multiply, this multiply, and this multiply, plus 8 additions, which would be these 4 additions, followed by these 4 additions to compute the final reduction of the matrix values. And you might be like, well, wait a minute, that's too many operations. Well, I am trading off multiplies for additions. And in some cases, this could be very useful, such as if you're designing an ASIC, or if you're designing an FPGA implementation of something like this. Those are some of the techniques that you do see actually even implemented in the good versions on GPUs right now, because there is some benefit when you go to higher dimensionality. Okay. So in some sense, this should tell you why GPUs are doing so well in this space. Because like if you hear deep learning these days, you hear, oh, I'm using these NVIDIA GPUs and so on. It's a program that has a lot of the same structure as dense matrix multiplication, which is the most arithmetically intense thing you can ever have. And so any processor with a lot of compute is going to do really well. So that's one reason why the GPUs are doing really good. It's basically like a graphics workload. There's tons of math. The other reason why is that most off-the-shelf implementations of deep networks on CPUs use the reduction to dense matrix multiplication that I just told you about. And they have not been heavily optimized using direct convolution or even some of these asymptotically better techniques that I have on this slide. The GPU libraries, the GPU companies have said, hey, this is something that's really popular in the world. Our products are really good at it. They spend a ton of time embedding these kinds of smarts into their libraries. So these days, if you took, like maybe a reasonably beefy, 8-core, 16-core CPU, and you benchmarked it against a high-end GPU, same network, the high-end GPU would probably be about a factor of 10 to 15, maybe 20, depending on what's going on, faster per chip. And that's not all because there's more math. It's actually largely because of better implementation. And there's a lot of people that have hand-wavy done this version of it on a CPU and can show that you could improve a lot of the off-the-shelf stuff by a factor of 4 or 5 pretty quickly, actually. So that number 15x is not fundamental in any way, shape, or form. It's a matter of both the flops and the effort. Okay, so I want to finish up on the other axis of how to make this stuff really efficient. So those of you that are mobile app developers might be like, this is super cool, right? Like I'm be able to do image processing or speech processing or beat Koreans at Go, on my iPhone. But there's a problem, right? Like these networks are big. So AlexNet, VGG, we're talking hundreds of megabytes of parameters to store these things. And so in some sense, you might be like, well, there's a lot of practical obstacles to deploying an app that has a 1 gigabyte download that's an iPhone app. That's a problem. There are other things where you could just say, consider the energy cost of evaluating the network in a future where you're trying to do always-on computer vision, let's say, on a drone, a low-energy drone, or on your iPhone, or like Amazon's Echo, which is plugged into the wall, but it's always listening to you, for better or worse. So if you just do the bandwidth cost of this thing, so I'm using some numbers from a recent paper where they just rounded up to 1 billion units, 1 billion parameters. Running at 20 hertz, remember we had this number 640 picojoules per bit from DRAM, per word from DRAM. That's 13 watts just to read the network parameters every time. That's not counting the compute in an arithmetically intense operation. So this is kind of like a non-starter, right? Like just evaluating the network over and over and over again will consume 13 watts just to read the parameters. And so as you can guess, there's a lot of interest in trying to shrink this 500 megabytes these days. And I'll give you a brief sketch of sort of what people are doing, and it's surprisingly effective, really, really effective. So one example is a lot of those 500 megabytes of parameters end up being very small numbers, end up being near zeros. So one answer is just get rid of everything that's close to 0. And that turns out to knock out 80 to 90% of the parameters, which suggests that there are certainly much more efficient training techniques because most of the parameters are not necessary. But that's a hard problem. And so then they, instead of representing these parameters, these filtering weights as dense matrices, they now need to be represented as sparse matrices. And they take very common storage formats that are common in any kind of sparse linear algebra or scientific computing. For example, if we wanted to store all the non-zeros in a row, we wouldn't store all of the zeros, especially if 90% of the cells were zeros. We could store an array that just had, just like your graph representation, value and column index, value and column index, and so on and so on. Now that means I can't just hand this off to dense matrix multiplication anymore. I have to rewrite my dense matrix multiplication for this irregular data structure, and that will be, that's what people are starting to figure out how to do. So one answer is that if we modify our training to try and push the training to get as many weights towards 0 as possible, we can cut out about 90% of our networks. Okay. The next thing we can do is for all the surviving non-zeros, we would prefer not to represent them as 32 bits. Maybe we can get by with something much, much less. So one answer would be to say, okay, let's just quantize and represent them as 16 bits. Represent them as 8 bits. There's even some recent work that's representing them as 1 bit. Because at the end of the day, you're just trying to get a correct answer. You're not necessarily, like, accuracy is only you want to predict yes or no or something like that. So one answer is just like use low precision math. And if you look at all the recent GPUs that have been announced, they actually all are adding back in. The push was always, oh, we need 64-bit math to handle supercomputing. The push is now, let's add in the 16-bit math from the mobile GPUs because we can do deep network evaluation much more efficiently, and it's just fine to do it in 16-bit math. Another answer is to be more sophisticated and compress, quantize these values much more intelligently. So imagine you had a weight matrix that looks like this. I could run a clustering algorithm. I could run, let's say, k-means on the weight matrix and assign every weight to a cluster. And if I had k clusters, that means I can represent this weight matrix, all the non-zeros, as a log k bits to describe a cluster, as well as the cluster center. So now I've basically learned my quantization based on the data itself. It's an irregular quantization. So the weights, the non-zeros, are not stored as 32-bit values. They'll be stored here as just an index into a cluster, and the value will just be the cluster center. So we've actually taken the non-zeros and forced them to share the same weights. That's essentially what's happened, right? And last, I can do standard compression techniques for like everything that's not a non-zero, I can just huff and encode that or something like that. Right? I can get a little bit more out by doing fairly simple stuff. And so here's an example of that big network that I was just showing you, 500 megabytes worth of weights. And these are all the layers. And this is a really nice chart of how much you get from applying these techniques. So this is the number of weights, not the megabytes. So you multiply this by 4 if this was a 32-bit weight. This is how many connections just get pruned because they're so close to 0. So this is the percentage of those connections. Oh, sorry, of that retained. Sorry, retained. Right, so like 4% in these fully connected layers are retained, which makes sense because everything in the world is not related to everything else. Then they quantize into 8 clusters. Sorry, to multiple clusters. So you have 8 bits to describe a cluster center. And for the fully connected layers, you can get down to 5 bits to describe the cluster center. So we have 32 clusters here and 256 clusters for the convolutional layers. This is if you add the Huffman encoding, so that's on average the number of bits per weight. And so at the end of the day, these are your compression ratio, or not ratios, but this is the compressed network is this fraction of the original network, right? So it's been fairly effective, right? 50x compression is effective. And if you look at the output is pretty good. So this is the output on the ImageNet image classification challenge, which is kind of like a very common benchmark of, given an image, does your network correctly predict which of 1,000 categories of objects are in the network? And so there's 2 ways to say how well are you doing. One way is to say, do you always predict the right answer? Or another way to say it is, out of the things that you think are the 5 most likely, is one of those the right answer? So that's why the error on top 1 is higher than the error on top 5. So 10% of the time, you get the right answer. Or sorry, 10% of the time you're wrong. Your top 5 guesses are all wrong. And if you actually notice, the compressed network in this case is actually doing better than the original network, which gives you a sense of sort of we're still trying to understand what we have learned and what we haven't learned. You can say that, oh, maybe the big network has been overfit to something, and the compression has actually kind of smoothed and regularized out the data, and so on. But 50x compression is a pretty big deal, right? Because that took 500 megabytes, to 10 megabytes. And so now all of a sudden, that whole network might be fitting in an L3 cache pretty soon. And so that's the only way that we're going to be able to get to sort of this real-time evaluation of these systems. So to close up here, it's 421, is the best performing stuff, The best performing architectures for deep networks these days are absolutely GPUs. It's for one fundamental reason, is that they have better, more arithmetic capability, and this is an arithmetically intense operation. The other reason is that the libraries are much, much better for GPUs than they are for CPUs right now. There's a lot of interest in designing new architectures that can do this stuff more efficiently. So you see conventional architectures like NVIDIA's newest GPU adding 16-bit arithmetic that runs at twice the rate of 32-bit arithmetic. So you not only save energy, you get double the peak throughput. You have Intel working on processors for supercomputing that are Intel hopes will be an excellent architecture to compete with the GPUs on this workload. And you have, really for decades, people have been trying to design FPGA solutions for accelerating neural networks. And now there's a lot of really serious effort to do that and to look at special purpose processors, especially in mobile, or maybe FPGA solutions for accelerating these workloads. So I'll talk a little bit next time about the frameworks that people are using, because I want to talk a little bit about how training works before we talk about some of those frameworks. So Wednesday we'll talk about parallel training, coming up with the weights. Hopefully this should shed some light on sort of how to interpret all of the jargon and all of the hype that's going on out there in deep learning.